with pleasure. It's my great honor to speak here. This is the title. So I'm going to talk about test ideals in this characteristic. We are the p-adic Riemann-Hilbert. So we have a lot of courses in this. So I'm just using their initials to. But let me just say it out. Right, say it out their name. So this is Bhargav Bhatt, myself. This is Zsolt Patakfalvi, Karl Schwede, Kevin Tucker, Joel Waldron, and Jakub Witaszek. So, all right. So let me start with giving you some motivation for this work. So our motivation comes from this the study of commutative algebra and birational geometry. So for the moment, let me just assume X is a scheme like finite type over a perfect field. You can say algebraic closed field, and let's say it's normal and integral. Just to avoid some technicalities. And so then, classically, so in this equal characteristic setup, we have this. If the characteristic is 0, so we have this the so-called multiplier ideal. So, okay, so let me just define this J of omega x. Omega x is the canonical sheaf. So this is defined to be the push forward of omega y, where y to x is a resolution. So this is the so-called the multiplier submodule. So it's a subsheaf of the canonical sheaf of x. And if the characteristic is P, so then there's an analog object of this. So we call this a test submodule. The tau of omega x is also a subsheaf of the canonical sheaf. So this is defined to be the smallest. Well, one way to define it is the smallest non-zero subsheaf of your canonical sheaf that is sort of stable under the forgive and under the well, that is stable under the trace map. This is the trace map of the forgiveness. Okay, so it's not obvious in this character P. It's not so obvious that this is this thing exists, but it's indeed the case, and you need some work. So, and this is what we call the test submodule. So, okay, so sorry, I need to point it out. So my title is called test ideal, multiplier ideal, but actually in this talk I will never talk about multiplier or test ideals. I will just work with the multiplier submodule and test submodule. So usually, if you want to get an ideal, what we do in this birational geometry is that you since we're in the normal case, you twist it by the canonical divisor or anti-canonical divisor, you get back to an ideal sheaf. And to do that, you necessarily work with singularities of pairs. And in this talk, I want to avoid those things, avoid those technicalities. We just work in this sort of simple setup, and those things doesn't play any role in later part of the talk. So I'll just work with the subsheaf of the canonical sheaf. Okay, so yeah.
So just small question. So in the characteristic 0 case, is it correct that the higher derived higher?
That's right. The higher ones vanish. I'll say. Okay, so why we care about these things? So first of all, I mean, so these things. So okay, so maybe I should say first one, you should think about these as some sort of measure of the singularities of x. So namely, okay, so basically, so J omega x and this tau of omega x, they have nice properties. So for example, so okay, maybe first I should point it out that if x is regular or smooth, and so then these are just the canonical sheaf itself. So J equals omega x. If x is regular. So some sort of, you can view this as some sort of measure of how far that your thing is going to be regular. Okay, and if you restrict to a divisor, I mean there are several properties. Let me just mention a few of them that can be stated here. So, for example, once you define such an invariant, you always want to ask, like, what happens if you restrict to a divisor, if you do some finite extension, birational extension, etc. And so, if you have a Cartier divisor, right? So you can restrict your I mean, you have this junction map. So let's see omega x. Right. So if x is smooth, then this is also right exact. But in general, you only have this you only have this exact sequence up to here. So there are some obstructions on the surjectivity. But the point is that if you right, so here you can look at this j or tau of omega. If you look at this subsheaf and then you restrict, so then you get the surjection. Okay, so in general, when you restrict it to a divisor, the canonical sheaf may not restrict to the canonical sheaf, but this one does restrict to it. Okay, so you could imagine, somehow this gives you some hope of doing induction in this higher dimensional thing. You restrict to divisor, and then you, instead of working with the actual canonical sheaf, you. Okay, so this is first property. But it's essentially local. So locally, if you restrict, you get a. And it also satisfies some global property. So, for example, it's well known that if you have a smooth projective, let's say over C, let's say you have a smooth projective variety, and if you take your canonical sheaf and take a very ample line bundle, if you twist it enough by the line bundle, actually dimension +1 power of the line bundle, your sheaf becomes globally generated. For example, think about the projective space. The canonical sheaf is all twisted by -d-1, and if you twist it by enough, actually it's an explicit bound d+1, so then your bundle becomes trivial, so it's globally generated. And of course, in singular case, this fails like badly, right? So you can have arbitrary, but if you work with this multiplier subsheaf or test subsheaf, that's satisfied, right? So if so the x is projective, and now is ample, so then this subsheaf of the canonical sheaf, if you twist it by this dimension +1, so then you get global generation. So as expected. So this is some sort of global, and these are not very difficult to show. So maybe I should say, so at least in classic 0, since Q already pointed out. So this j of omega x is actually satisfied to that vanish. So namely, if you pick any ample line bundle, if you so this one has no higher cohomology after you twist by any ample line bundle. Okay, and this really, if you think about it, this is actually not so hard to show. It's basically coming from you pull back to the resolution, and then it's really just commutative Liouville vanishing on the resolution. Finally, let me also mention, as I already said it, so once you define such an invariant, you always want to study how they behave under finite or birational morphism. And so they do behave as expected. And in fact, so this multiplier or test submodule, they can be computed using alteration. So so this is the same as you intersect over all alteration, and you look at the image of the image of the trace. Let me call this is F. Okay, if you take this intersection, then you do get this one. And in fact, this intersection also stabilizes. This is also the image y, omega x, for any single, but y has to be very, very large. And we have, I don't think we have control, but this is just, it's okay, and maybe I should say etc. So there are many other properties. I don't want to list all of them. Some of them you do have to go to singularity of the pairs to better state them here. So I will omit the other thing, but I hope this already gives you some feeling that these sort of objects are of interest in the study of algebraic geometry. Okay, and so the question that I'm gonna discuss today is, can we find the analog of this multiplier subsheaf or test subsheaf when x is not over a field, when x is defined over a DVR, for example. Okay, so that's the main question. And
wait, so sorry, so this last thing is kind of obvious in characteristic 0, right? It's the pair for tau.
Right. This is yeah, you are. It's obvious in terms of 0 because it's by definition. Okay, and so before I move on, so let me just okay, so I want to, so the main interest in mixed characteristics, so I want to mention some commutative algebra background. So I want to recall you this. There are some recent breakthroughs in the mixed characteristic commutative algebra by Andre and Bhargav. So let me just mention so the statement is actually quite simple. So if you have a Noetherian local ring, so then the theorem says, so then R admits a big homotonic. Okay, so let me explain what does this mean. So B is called big homotonic. So there are several ways to define them. I'm just going to take one of them. If every system of parameters R is a regular sequence. And let me just need some non-triviality. Otherwise, just take the 0 or the fraction field, whatever. So you need some non-triviality condition. Okay. I just want to point it out if you are comfortable with the local cohomology. So this condition implies, for example, the lower local cohomology of B as 0, and the top local cohomology is not 0. Okay, so we know that local cohomology captures the depth of a module, at least in the Noetherian setup. So this is sort of like saying this huge object B has depth, the largest possible. So that's why the name big. So the big just means like these B's are not necessarily finite generated, not necessarily Noetherian. Actually, in most cases, they are not Noetherian. Okay, so Hoxer-Hünicke, let me just Hoxer-Hünicke to the equal characteristic case. So this is back in the 1990s, early 1990s, I think. And Andre did the mixed characteristic case. Oops. And furthermore, let me mention this will play a role in the later part. So in this residue characteristic P, or this either characteristic P or mixed characteristic, so you can, so not only this big Kolmogorov algebra exists, you can actually take them to be perfectoid. One can take E, perfectoid algebra. So here perfectoid is the integral perfectoid. Is the definition follows from the BMS definition. So okay, so this is for Andre. Also small. And so finally, let me point it out. So there is actually one explicit construction of the big Kolmogorov algebra. So functor unity show that in terms of P. So then, so this is the, oops, sorry, I need some assumptions here. And so suppose like Rm is now a complete domain. So here complete, I mean M-adically complete local domain. So then in this setup, functor unity shows, sorry. Sorry, let me just if the characteristic of R is P, and Bhargav shows that the mixed characteristic. So then all you need to do is to take the p-adic completion. Okay, so R plus is the absolute integral closure. It's the integral closure of R in an algebraic closure of the fraction field of R. Okay, it's still very huge, but it's a very explicit object. It's also, you can view it as, so R plus is just you fix an algebraic closure of the fraction field. R plus is just the direct limit of all the finite extensions of R inside that in this table. Okay, so these are some like recent progress in the mixed characteristic commutative algebra. So what can we do without seeing why these big Kolmogorov algebras are useful? So here's a definition that I made with Schwede several years ago. Is that once you have this B, so what we observe is that you can define, I mean, at least locally, you can introduce a test submodule, so sort of having the good analog of this local properties. So, so for simplicity, let me say this is local domain of residual characteristic P. Okay, so then, okay, so and so now we know there exists a big Kolmogorov algebra. So let's big Kolmogorov R algebra. So then we define the following. So we define this tau B of the omega R. So this is a canonical module. We define it to be the image of the tau B to omega R, and then you do this evaluation at 1 of. All right, and so, well, it depends on the choice of B, but we can also make it sort of not really depends on B. For example, you can use this Hawkes unity or Bhargav's result. So you use this explicit B, but that sort of does not depend on B. But another way you can do is that you manually make it canonical. You let me just introduce this. This is curly B. We define it to be the intersection of all B perfectori of this tau. Okay, and we show this intersection stabilizes. So this is equal to tau B of omega r. 1. Of course, B has to be very large. We don't know how large it is.
So B runs over all perfectoid.
Perfectoid
big CN.
big CN. So that's sort of one subtlety, like I emphasize this, because without, actually, this is sort of interesting. Without this, we cannot show that this is stabilizes. So
If you go to, if you allow it, take all big CN.
if you take all big CN, of course, we expect this is still stabilizes, but we don't know how to prove, turns out. So that's okay. So this is of course, this is very local picture, because I work with a local ring, and and I'm analytically complete. But basically, the reason is that so these objects, so there are some local version of the tau and j that I wrote on that board, and we can show actually, and it's actually not so hard to show that they satisfy the local they satisfy the expected local properties that j and tau that you expect that they have to satisfy. Okay, so basically the point is that this big Macaulay algebra just provide us the vanishing that we need in the arguments. Okay, yeah.
Is R still a Noetherian?
Right, Noetherian. Oh, sorry. So here is Noetherian. Sorry. Yeah, I have to put this because later on the rings are definitely not going to be Noetherian. B is not Noetherian.
Sorry, just to clarify, do you need any additional conditions beyond the theory?
For which one?
It's complete.
Complete, automatically complete.
So what are the R's for which you would expect this to be all of omega R?
Those R's are some sort of close to rational singularities in characteristic 0. So we expect it to be the same. Yeah.
So certainly when R is right there.
Certainly where, yeah, maybe I should say when. If R is not if and only if. That's a good point. Okay, so basically, locally, I mean, I think we believe this is. I mean, you can use a sort of the big B, or you can use R plus. So most of these are enough for the local applications to commutative algebra. But there's an issue here. So namely that if you stick with this definition, or this one, I already tell you that just some 1Bs, right? So the issue is that well, we don't know whether this one commutes with localization. I mean, whenever you define an invariant in commutative algebra, you always, the first thing you ask is that whether this thing commutes with localization, and that's not clear in this setup. Of course, I mean, I only define it for complete. If you localize, you lose this, but you can complete again, or you can also introduce this definition for accident or whatever, and you ask the same question. But basically, I want to show these things. It's not easy at all, or not obvious at all, that this thing commutes with localization, basically because this B is large. So this harm set, if you localize it, is not the harm set after you localize, right? Because you lose the B is not finite. Okay, and so the question we want to ask is that whether there is some sort of version of global analog of this, or can we introduce a version that can be defined globally such that at a completed stop, it agrees with this tau B we introduced here. And let me also mention a remark. So everything is defined when the residual characteristic P. So in particular, when R has characteristic P, you can define this, and the connection between positive characteristic, there is indeed, I mean, let me just put it here. Say X as over B as in the first port. And so then you can define this tau omega x by the Frobenius. And so then you can you take a point, look at the completed stock at that point, and then it does agree with what I wrote there. Right, so this is the same as you use R plus, and it's also the same as you use larger and larger. So this is a result of things. Okay, so in terms of P, there is a sort of, it just tells you there is a globally defined object such that at the completed stop, it agrees with this this tau R plus or tau B or any. So since these are the same, so you can use any B in between R plus and the ultimate B. Okay, so now the question is, what about next term?
A local ring was a domain.
Oh, sorry. Normal integral. So for just to avoid. I mean, you don't need, but okay. So, further question? Now I'm gonna move on to a setup of the rest of the talk.
Wait, sorry, does the characteristic P thing also work for any B or only B sufficiently big?
B sufficiently big. For example, if R itself is called Macaulay, you can just use R. Yeah, okay. Further questions?
Sorry, can I just ask you, is a question, about the previous question, so can you take any V which is a perfectoid big C on algebra to define, like, will you get a different choice for?
Okay, so Smith's result says, well, at least locally, using R plus and using the B does not make a difference. So that means right? So it's clear from the definition that larger B results in smaller, tau, right? So this one is obviously contained inside here. And if these are the same, so then any B in between any B bigger than R plus will give you the same answer. But there are smaller R's in some cases that won't give you the same answer, even if you throw in this perfection. For example, if R itself is Cohen-Macaulay, you can take the perfection. That's a big Cohen-Macaulay argument. So you do the perfection, it gives you a different object, not the test idea. All right, so now, okay, so the setup for the rest of my talk, maybe new setup. Okay, so now for simplicity, let me just assume X is projective over ZP. I mean, it really doesn't matter. You can do you can do any complete. Okay, so now we can enlarge the base. So we define B infinity to be you enlarge this to a perfectoid base. You have a completion, and so then we base change this to this perfectoid DVR. And so note that So now this is a sort of a nano-theorem base, but at least the generic fiber is a nice thing. So if you generic fiber is finite type over a field, right? So this is projective. And this is a field of characteristic zero. Okay, so the generic fiber is projective over a field. All right, so in this setup, so we have the Riemann-Hilbert functor that introduced and studied by Bhatt and Bhatt-Lurie. So they defined this in much more general setup, but I will just cite what I needed for the work in this setup. So Bhatt-Lurie, so they told us that there exists a functor it's called the Riemann-Hilbert. So for what all we're going to need for this theory is that it takes the bounded constructal sheaves on this generic fiber with ZP coefficient. And now if the value of this lands inside the almost coherent complex on the perfectorization of this X infinity. Okay, and moreover, so the key fact we're going to use about this functor is that it is left exact with the perverse T structure on both sides. So left exact T exact with respect to the perverse T structure on both. Let me just explain a little bit about this. Of course, so first of all,
Does almost coherent mean pseudo-coherent?
in this case, I will say, so in this case, it's just since I'm working with bounded, it just means each cohomology is almost finally presented over this over X infinity, O X infinity.
Yeah, it's almost in the sense of almost math, not not pseudo-coherence.
Yeah.
We're going to be talking about almost perfect complex.
Okay, so let me explain so first of all, as I already mentioned, this is just a projective over a field of characteristic zero. So the perverse structure here is just you can define it as usual, using the support condition on the cohomology. But we are working with the ZP coefficient. There are some shifts that you have to be careful. So let me just perverse structure. Let me just explain this a little bit. So first of all, the left side is just defined usually. So I think there's a +1 here because we have just the ZP thing, and similarly, cohomology of this support is inside.
Wait,
Oh, sorry. And the right hand side is so this is there's a purpose structure on this almost coherent, but this is actually even more simpler. It's just the Grothendieck dual of the usual P structure. Since the Grothendieck the usual. So namely that if I have a K on the right hand side, it's inside the dp equal to 0, respectively. If and only if you hum, after you just hum K to this relative dualizing complex, is in dp less than almost. Okay, so it's very simple. You just because I'm working with almost coherent, so you can just when you hum to this thing, it's also almost coherent. So you can think of you can just work with the usual P structure. Okay, and the upshot of this. So how are we going to use this? So as I said, the key property that's relevant for us is this left T exactness. So it's coming out of this is that. So I just want to. So this already, I think this already shows up in Bhargav's paper on this absolute integral closure. That is namely, if you apply this functor and you plug in a perverse sheaf, okay. So then it gives you, of course, this is left exact. It gives you something in dp equal to 0, and I want to say this one is some version of almost homoconic complex up to shift. Okay, so let me just explain this a little bit more. So what does it mean that some k is in like dp equal to 0 on this right hand side? So that means, remember, that's if and only if you the dual is in D less than D. All right, but now okay. So every almost. So here K is almost coherent. So what we imagine is okay. If this is really coherent for the moment. I'm just giving some intuition. If K is really coherent, so then K is coming from some finite level, all right? And on the finite level, you're in the Noetherian case. And in the Noetherian case, let's see what is this dual. So the local duality tells you that let's suppose it's just really coming from the base. So this is dual to R gamma x. So let's say localize it. Let's work at a point. Okay. So this is due to the local cohomology of Kx. All right. So saying this is this is connective. It's the same as saying this one is co-connected. Almost. All right, and so basically that's just saying if you do the appropriate shift, so this gives you D equal to the dimension. Almost. Okay, so a local cohomology is a measure of depth, right? So the depth, it's cohomology if and only if there's no the local cohomology vanish before the dimension. And this is exactly saying this object has the desired vanishing property for local coordinates. Okay, and so that's my like a very rough explanation of why this thing holds.
So there in this, the bottom line in front of you, there should not be P.
Right, I think I'm pretty sure I made a mistake. Yeah, there's no P. It's the do of the standard. Yeah, sorry. Okay, so now with this thing, so now I can introduce our definition of the calc. So basically, so now you see, I mean, we need to plug in some purpose shift to give us this almost co-Macaulay complex. And I guess this functor, I'm still learning this, so there's I think the only example that I can write down at the moment for me is if you plug in the structure shift or the constant shift, to give you the structure shift of the perfectualization of the structure shape, and you can write down more examples by, because they also show this proper push forward compatibility. You can if you take the constant shape upstairs from finite cover, you can also write down some explicit formulas. But beyond this, I don't know how to write down explicit. At least the thing that we are interested. So, but anyway, so to apply this fact. Basically, we are looking for some purpose shifts that give us this almost co-Macaulay complexes, and so the standard way to get purpose shift is that you take open affine smooth. And so then you push forward the constant shift on U. So this turns out this is purpose by a version of RT minus ZP coefficient. All right. So the wait.
Shift.
Oh shoot. Yeah, you're right. All right, so now let's look at what's going to happen, right? So we have our structure sheaf, and that maps to the perfectualization. And this, I already told you, this is the Riemann-Hilbert ZP. And this maps to this. Okay. And so this is some almost homework. I think the shift, they should line up. So this is almost homework. All right, so now let me keep this definition here. So our definition is pretty similar to what we expect to see here. So instead of putting in a B, we just plug in this object. That gave us some object, but now this is defined globally and is going to be compatible with localization. So I'm just going to give the definition here. So, here's the definition. Okay, so I'm going to work with that setup. So I'm going to define tau. Sorry, first of all, not yet. So first of all, we define this at the infinity level. And how we define this is very simple. So we have this map from the structure sheaf to this almost Macaulay complex. We just dualize that. Okay. you do it like that, you get a map from R harm of this RH. Okay, so there's a map from here to this space. Okay, it's the corresponding dual of the map. And of course, we want to get a sheet, so I have to take cohomology. Okay, and now we take the image. Okay, so I hope it's because I have two definitions on the board. So this is evaluation 1. So right, so this is, I hope this one and this one put in this is pretty similar. So instead of using an actual non-Noetherian big Macaulay thing, we're using this. This is still not a Noetherian object, but this is close, right? Because this is almost coherent, very tiny. And it's coming from this X thing. Okay? Yeah.
Sorry, could you say again what J is?
J is this embedding. This is J.
And what is U?
This U is an open affine regular. That's right. U.
So why can I not take U to be the empty set?
Why can U to be what?
You said it is open affine and regular.
Oh, I'm sorry.
So just to clarify, so is the claim that the choice of U is independent of like the answer that you get?
It's that's a good question. So honestly, you should plug in the intersection the IC shape here, but that doesn't matter. Once you take the dual, it doesn't matter.
Right, but in particular, the choice of U doesn't matter.
Right, the choice of U doesn't matter. Okay, so this is, we define this at the infinity level. So finally, let's just, well, you know, so now everything is on X infinity. So to go from X infinity to X, right? So the standard way to do this is you want to apply some like, so because X infinity is a limit, some sort of like a finite extension of X. So to comes down to X, you need some like trace to get it back. Unfortunately, there's no trace because this is not finite. So we sort of introduce a trace-like method that is very simple. So there's a map from here to here, but this is really, since I'm in this relative version, this is really this one tensor with V infinity. So T really induced by T from V infinity to V by sending this basis element P to the 1 minus 1 over P to the E, 1, and other basis to 0. Okay, it's some sort of like trace line. Okay, and so then, sorry, we define this how.
What is E here? 1? Or...
Huh? What is what? Sorry.
E.
E is an integer. E is an integer.
For...
Right, because V infinity. Is this still on the board? V infinity is basically joining OP per root of P. So those are particular bases and 1 P to D minus 1 divided by P to D. Those are in V infinity. So I mean, it's really okay. Why we do that? It's very simple because if you look at V to VE, if you look at ZP to ZP, P to 1 to VE, if you look at this is V to this is VE, so then the trace map sending that one to 1 and all the other bases to 0. We sort of want to choose them in a compatible way, so we send all those particular things to 1 and others to 0. And that's compatible on all these, it turns out. So
this is colimit of traces.
What?
Is this colimit of traces? It's
Right, some kind of a normalized, colimit of normalized traces.
Right, and so then finally, okay, so this, finally got to our definition. So tau RH of omega x it's just t. You apply t to this tau omega RH at the infinity level. Okay, and so that so now of course we need to prove a lot of things. So this is, I mean, the definition is pretty intuitive. It's just it almost sounds like it ought to satisfy these properties, but this requires proof. So the result is that. So first of all, this. Okay, so let me just say, right? It's at least it's for the. Oh, sorry, I erased that. But at least for the property that I listed on the board, we can show exactly the same. So first of all, power H is the whole thing. It's X is regular, and it satisfies the. Okay, so I'm not going to write it down, but satisfies the restriction property. If you restrict to the divisor, it behaves as expected. And global generation or effective global generation twisted by this very ample line bundle to the dimension +1 is globally generated. Okay, it can be computed by one alteration, but this is still there are some subtlety there up to p perturbation. Up to p perturbation. So basically, I'm not going to be writing down. Instead of looking at just at the trace map from an alteration to X, you have to multiply that map by p to the epsilon for epsilon sufficiently small. And if you do that, that does give us this power H. Okay. All right. So finally, let me mention. Okay. So so now we have this object satisfy these nice properties. How do we compare the stuff? Okay. So okay, so we want to relate this to, for example, to this tau b or tau r plus. That r plus is a specific big commutative algebra constructed by Bhargav. So we want to, and so first of all, okay, so under the same setup, if you take a point on the generic fiber, so sorry, let me just say, so it turns out that the generic fiber just this object lineup exactly agrees with the multiplier idea. Right? So if you invert p, that gives you exactly the multiplier. Okay, so for points on the generic fiber, you get what you expect it to get. Okay, and so but for points on the special fiber, so we want to sorry, I erased the Smith's result. We want to compare this power H at the completed stock with the tau d or like tau r plus, right? Something like that. And the result we get here, this is still you know, the results here are still like not totally completed here. So what we can show is that this is the same. Okay, let me say R is OXX completion. So this is a complete local domain of mixed characteristic now. So this is equal to tau R plus hat. So this is a particular big commutative algebra, and omega R. But you have to do a small perturbation. Okay, so this. I'm sorry, I don't know. We have to work with pairs. But what does this mean? So remember, if you define this tau r plus, you have r plus evaluation 1 to omega r. But with that p to the epsilon, it's very simple. You just evaluate at p to the epsilon. Okay? P to the epsilon makes sense in r plus. Right? So of course, in practice, we always expect that this sort of small perturbation will not change anything. This is the case in character P and for test ideals or multiplier ideal, this is almost a trivial fact. Okay, but here there are some subtleties. We don't know how to get rid of this, so we keep this for the moment. If you use this intersection of OB, so that is a different story. So then we have to perturb this side. There exists Cartier divisor such that for any close point on the special fiber, if you perturb this a little bit, okay, and the completed stock is equal to tau d. Okay, so again, perturb just means instead of usually evaluate at 1, you evaluate at this. Let's say h is defined by some element to the epsilon power. Of course, that element may not exist in X, but what you do is that you take a finite cover and do the construction there and then push forward. Okay, so that's how you define. I'm sorry, I don't have time to define this for pairs, but it's something like there's only one way you expect it how this is. Okay, so and clearly, so I guess this is always, I mean, perturbed version. This is always continuous at here. So this is always continuous at here, and this is the same, and this is always up to perturb. It's gonna smaller. Okay, so you got this all the way, including this. But so now the missing piece, like at least for me, we don't know whether these are the same. Okay, and if this is the same, you can get rid of all the perturbations. Okay, and so this is indeed true in character P, and that's a result of Carey-Smith formulated in this way. But this we still don't know. But we have to. In practice, this not create too much problem because we can just use this. We can just build in the perturbation to define. For example, I think in our paper we want to really define the ultimate tau be this one. Okay, so that satisfies all the desired parts. Yeah, sorry, I will stop here.
Will this satisfy some other properties of multiplier deals like subadditivity or?
Right, it will satisfy subadditivity. If you have to define it for triples and then it satisfies subadditivity.
Semi-continuity or something?
Semi-continuity, what do you mean? So
Maybe we should talk after.
yeah, subadditivity, yes.
So how important is that specific V infinity that you chose?
Not really. I think you can also use any, and you can also use V plus, and then you run your functor for that. But of course, the trace you have to define it, adjust it slightly.
Is it possible to write tau RH as some type of intersection that stabilizes to give your definition?
You can, but the point is that you can on the nodes you can just define this. You can define this. Okay, you can define this tau to be just you use all the operations, right? And you image it. You can write down such a definition is independent of the characteristic. But the point is that with this definition, I think we still don't know whether this one stabilizes. So we don't know whether this commutes this localization, for example.
So in the RH, like you say, it's only left exact.
Right.
Why is not right?
Okay, I guess I will leave to the authors of that paper to answer this.
Is there like an easy example?
I think the statement was slightly incorrect as written, so let's discuss it afterwards. I think it formally follows from what was written that if it was left exact, it would be right exact. So, okay, yeah.
Wait, what? Which one is incorrect? Sorry,
Sorry, the definition of the perverse T structure you gave was not for modules of the perfectoidization, but only after you forget the perfectoidized structure on X infinity itself. But where your code was for the,
Right. What I wrote is for the what?
sorry, let's discuss it after.
Okay,
It's a
okay,
technical
sorry, yeah. I thought I'm only working with almost coherent, so that should be fine, but.
And it's about the coefficients, OX infinity versus OX infinity per factoid. The right part of the T structure remains the same, but the left part changes.
Can I ask you, so I just had a basic question, so, it's, back to an earlier question, so, can you say anything about the class of rings for which this, this object is the same as omega R?
So in, oh, you mean in this mixed characteristic?
Yeah, so is it correct, is this something like, you said, you mentioned the word rational singularities in characteristic 0, and
It's F rational in characteristic P, and in mixed characteristic, we call it BCM rational, but it doesn't give any, well, we just define it to be those class of rings such that this is equal to the omega R. It doesn't, yeah, I don't know a good answer. I mean, I don't know a good characterization in terms of other invariants.
In low dimension, is it possible to classify?
Right, in dimension 2, there's a classification. Right. It's basically in dimension 2, characteristic P bigger than 5, and so a perturbed version of this is just chaotic.
Sorry, but in this mixed characteristic.
Right, in mixed characteristic, right.
Is there any more questions? Oh, Lars? Oh, no, sorry, there was a second one again.